Allora, questo è un video girato in Russia nel 2013 a Celiambinsk in Siberia, dove appunto un asteroide che in cielo aveva nello spazio una dimensione di circa 20 metri è caduto sulla Terra e ha provocato perché l'onda d'urto che è stata creata dall'esplosione dell'asteroide nel cielo ha rotto vetri, finestre, ha rotto, non so, ha fatto cadere magari delle edifici. Alla fine che fa? Esplode. E quello che si crea con l'esplosione c'era un prezzo complesso alla fine un po' di no, che appunto può provocare rotture anche di vetri. Quindi puoi immaginare succedendo fuori, avvicinandoti ai vetri esplodono in faccia, e questo è quello che è successo più o meno in questo evento. In particolare lui non era stato scoperto da e non lo vedremmo arrivare. La stessa cosa, il telescopio guarda verso il Sole e non vede nulla. Quindi noi non siamo riusciti a vederlo prima, poi stiamo parlando ormai di 12 anni fa, quindi anche la potenza del telescopio era diversa, la tecnologia era diversa, anche la nostra conoscenza era diversa, per evitare proprio questi effetti anche di geometrie che impediscano di vedere gli asteroidi. Cosa è successo? Quindi per questo asteroide è caduto in un lago ghiacciato e ha lasciato quello che viene chiamato un cratere. In questo caso un cratere diverso da quello a cui siamo abituati, perché non era a terra ma era in un lago ghiacciato, però questo ha permesso di identificarlo molto facilmente, perché se invece fosse caduto in una foresta o nel deserto probabilmente sarebbe stato più difficile da trovare. E quello che vedete lì è la parte dell'asteroide che si è conservata dopo il passaggio in atmosfera. Quindi quello è quello che è arrivato a terra. Sicuramente ci saranno stati altri frammenti, ma quella è la parte principale, e pensate che quel sasso pesa circa 560 kg. Quindi è bello denso. Altri in Perù di abbiamo voluto mettere qui invece a terra ne ha creato un cratere di circa 1 chilometro. Devi capire un pochino un cratere molto più 66 milioni di anni fa. Cosa è successo 66 milioni di anni fa? Bravissimi. Quindi questo è il cratere dell'impatto dell'asteroide che si pensa abbia causato l'estinzione dei dinosauri. È un cratere che sta nel Golfo del Messico. Questa è una rilevazione fatta da satellite della gravità del cratere, quindi da lì si vede che c'è questa forma, perché ovviamente se voi andate lì è talmente grande che non è che lo potete vedere a occhio, poi una parte è sommersa e sott'acqua, una parte è sommersa e una parte è a terra, e quindi si è potuto rilevare questo cratere soltanto una volta che abbiamo avuto gli strumenti per farlo, quindi i satelliti. Con diverse tecnologie si è trovato che il cratere esattamente lì è fatto a forma di cratere. Ok, ora iniziamo le attività proprio pratiche. Sì, adesso ne parliamo di questo, assolutamente. Quindi possiamo iniziare le attività di gioco, quindi non so se voi volete spostarvi per la sessione di domande. Ora, come dice il vostro compagno, questa è la Luna, ovviamente non è la Terra, e questo è un cratere da impatto di un meteorite, di un asteroide.
Okay, we're ready for the Q&A, and we hope the connection will be better. We're in another room. So sorry. It doesn't. So sorry. Okay. Here you are, Mr. Charlie.
Yes.
Okay. Can you introduce yourself?
Yeah.
There. Okay. Just a moment. Have you heard me?
Yes, dear, thank you.
Okay. Okay. Just a moment. The connection is maybe will work in a few seconds, maybe, because I'm with you on my mobile phone. Okay, I give you my mobile phone. Okay.
So,
In English?
okay, hello everyone.
Yeah. Yeah.
How are we
Okay.
all? Okay.
Can you hear them? No. So
Yes, we can hear. Thank you.
okay. Maybe this way. Are you there?
Yes, we can hear and we can see you.
Okay.
Okay, great.
Okay.
Thank you. Okay, hello everyone. Hi, my name is Charlie, and I'm a young graduate trainee working here at ESA at the Planetary Defence Office. So it's lovely to have you all today, and I think you've got a few questions for me as well.
Okay. Are you ready for the first question? Okay.
Chiama la scuola terza aprile comprensivo.
Okay.
Okay.
The connection is not good. So sorry. Okay, the first.
La terza aprile comprensivo.
Okay, the first.
Okay, let me introduce myself first.
Okay.
So, hello everyone. Another member, another one to join the group today. I'm teacher Francesca Virfelice from Chieti, Italy. So I'm going to read the first question. Okay, so from class 3B, Comprehensive Institute Portella della Ginestra. So, what is the name of the office that protects the Earth from asteroids?
Yeah, so you may have heard in that brief introduction Laura gave in the other room that the office here at ESA that protects the Earth from asteroids is called the Planetary Defence Office. And our job is to observe asteroids and find them in the night sky. Then once we find them, we need to track them and monitor their position and keep an eye on them with our telescopes. And once we have some observations of the asteroids, we then have to compute the orbit and compute the trajectory to work out where these asteroids are going and work out if they're potentially dangerous. And if they are dangerous, then we may need to take a mitigation action to do something to reduce the threat of the asteroid as well. The main operational center of the Planetary Defence Office is the NEOCC, which is the Near Earth Object Coordination Center, and that's based right here in Rome, and it's where we're live streaming from right now, and this is where the main hub of the activity is. It's also worth noting that NASA and some other institutions, such as the University of Pisa, have their own program to monitor the threat of asteroids and their own software to do that. And between us, we independently discuss and verify our results. But ESA's office is the Planetary Defence Office. Okay, next question.
Okay, next one is from Scuola Secondaria Vicentini, from Katie. Please do your question.
Hello, we are ready.
Hi.
I'm here, Nicholas. Hello.
Hi, I'm Nicholas, and we are Vicentini della Porta. And my question is it possible to direct an asteroid into ocean?
Okay, hi Nicholas. Thank you for that question. That's a really interesting question. So into the ocean, the answer is technically yes. However, is it a good idea? Might be the other question. When you deflect an asteroid or move it, it's very hard to do it precisely. So often, if you were to redirect an asteroid, then it might be tricky to know where exactly it's going to go. So, for example, if you deflected the asteroid close to Earth, if it landed in the ocean close to shore, it might cause big waves or a tsunami or something like that. Or even worse, you could deflect it too much and it ends up going somewhere else on land and over another city. So at the moment, it's a very risky idea, which is why we don't tend to think about redirecting it into the ocean. Often the best course is to redirect it so it goes as far away from Earth as we possibly can. This has already been tested. If you've heard of the NASA DART mission, which was where they took a spacecraft traveling really fast and hurled it into the side of an asteroid to see if they could change its orbit. This method is called a kinetic impactor because you're impacting the asteroid with something with lots of kinetic energy, something that's moving really fast. And if you do this with lots of time before the asteroid is meant to come close to Earth, then even a small nudge by hitting the asteroid with your spacecraft can be enough to move the asteroid far enough away from Earth by the time it comes close to Earth. So this is at the moment our preferred method to deal with asteroid threats, is to see it very early on and then to nudge it out the way. If the asteroid was spotted very close to Earth, then that might be more tricky because we'd need a lot of force to push it out the way of the Earth. And that's when we consider using other measures. So the answer to your question is yes, it could be possible. However, it's very uncertain. So at the moment, we don't have the technology to do that precisely, and it could be risky. So yeah, thank you for that question.
Okay, thank you. Thank you, Katie, Istituto Vicentini. So next, Romania, calling Romania.
Hello, can you hear me?
Yes, we can.
Hello, I'm Alex, and we are from Liceu Teoretic Emil Racovița. And these are my questions. How do you detect asteroids? How do you calculate how fast they are traveling? And what about the diameter?
Yeah, hi, Alex. So thank you for those questions. And yeah, so a lot of good points there. So how do we detect asteroids? So around the world, we have these huge telescopes that are constantly scanning the skies every night, looking for these asteroids. So these are based in really exotic locations like Chile, South Africa, all over the world to cover as much of the night sky as possible. And what they're doing is they're taking pictures of sections of the night sky. And they're comparing two pictures side by side. And the idea is that you're looking for a very small dot to move between the images. If you think about when you take a picture of the night sky, you're going to have all the stars, and they're probably going to stay in the same place. The stars aren't going to move, they're going to be fixed. However, something like an asteroid, which is moving very fast, it's in the solar system, not like the other stars, so it's very close. That's going to be moving across the image between the pictures that you take. So astronomers look really carefully in the images to see these tiny pinpoints of light that are moving across the image. And if you can see a little dot moving across, then that's a sign that you may have an asteroid. This is where I think the word asteroid comes from. I believe it comes from the word to a wandering star or something like that. So once you've found the asteroid, then we need to work out some properties of it. Like you said, the speed. To do this, we do determination. And this is a very clever set of maths, which is 200 years old. And the idea is when you have your observations of the asteroid in the night sky, you can imagine these as little dots, little points in the night sky where you take your observations. We need to fit the trajectory, fit a line through those observations that matches it the best. So all objects in the solar system move in big orbits around the sun. They move in these huge ellipses as they sweep out their journey around the sun. And when we're looking at the asteroid moving, we're looking at a little teeny section of that big orbit, that big ellipse as it travels round. And so we need to find what curve, what little section of that orbit fits those observations the best. And so to do that, we have some very clever maths called orbit determination, which you can look at more if you want. It's quite complicated, but it's very interesting. And that gives us the full orbit of the asteroid. And from that, we get things like the speed, how far away it is, how fast it's moving, all of these properties. At that point, the orbit is quite uncertain. If you only start with 3 observations, then that line that we fitted, that trajectory, is still quite unknown. So it might be moving with a bit of a different speed. So we have to take more observations to then improve our estimated trajectory and orbit. And that's how we work out and refine things like the speed. For the diameter, this can be very tricky. When we have the image of the asteroid, in the image, all it really is a little dot of light that's moving. You know, if you look at that little dot, you can't see any surface detail. You can't see its shape or anything like that, or even its color. So really, we have to try and guess its size just from how bright it is. If you imagine a very bright object, we probably expect that it's very bright because it's quite close to us. However, there's a lot of other things that might make it bright, such as if the object is very bright on its surface, if it's very white, that means it's going to be very reflective compared to something that's very dark and very dim. So you have this problem of an asteroid that's very big and dark might appear just as bright as something that's very small and very reflective, very bright surface. So that's why when we give the size of an asteroid, it's often given in quite a range, because these details, such as how bright the surface is, we often don't know very well. So the diameter is estimated from its brightness, once we know how far away it is, and then we have to make some kind of assumption as to what the surface looks like, and that allows us to give a range how big the asteroid is. So yeah, I hope that answers your questions, and thank you very much.
Thank you too. Bye.
Thank you. Now, please, Greece. Are you with us?
You ready to ask? Okay.
So, second primary school of Skiathos, Greece. Hello. No.
Okay, can you read it, please, for us?
Okay. Sure. So, what are some strange things you have seen happening, so to say?
Yeah. Yeah, that's a really fun question, actually. What are the strange things that we see? I mean, I would say, thankfully, on the whole, asteroids tend to behave quite normally, as we'd expect. Thankfully, the laws of physics that people like Newton came up with 200 years ago are very good, and they're very good at predicting where the asteroids go. So on the whole, they behave as reacts. However, there are lots of strange things that happen when we're observing these objects, and lots of strange occurrences. One of the biggest problems we have at the moment is things like satellites and space debris. So these can be broken bits of satellites from satellites that have been destroyed long ago, or even just functioning satellites in the night sky. And when we're looking with our telescopes for these asteroids, sometimes these satellites come into view, and they can look a bit like an asteroid. It's bright and it's moving very fast across the sky. So sometimes our astronomers look at these and they think, "Oh, that might be an asteroid." And these can be a bit strange because they might be moving faster than we for asteroids, wrong or a bit difficult. So for example, if you think about a satellite, it might have lots of big solar panels on it. And these can be really bright when they reflect a lot of sunlight. So we had an example last year where we discovered this 15 a city to hit head on. So this was a very dangerous object, and we did some more observations, and we determined that it was actually a satellite or a probe that looked like an asteroid. It was mimicking this. So sometimes things like this can appear really strange when you think, whoa, how did this really dangerous asteroid just appear? Why didn't we see it earlier? But really, it's just a man-made object. So objects like that can appear very strange, and they're often very puzzling because they have very weird orbits that don't look like normal asteroids. And so these are things that we need to be careful of and watch out for. Yeah. Thank you.
Thank you. So, have we got some more time to make 2 more questions?
Yeah,
You've been so kind. Thank you so much. So, there's another question from Romania. Again. Thank you.
Hello. Hello again. I'm Marisa. And my question is, how do you calculate the trajectory when the asteroid is so far away?
Yes, thank you for that question. So how do we work out the trajectory when the asteroid is so far away? So really, I think the essence of this question is that even when asteroids are really far away, to determine the trajectory is still the same. As long as we can resolve that tiny point of light in the image and we can see it moving, and we can take its position in the night sky, then we can do that method of orbit determination and do the maths to work out where it's going to go. The problem becomes sometimes when asteroids are really, really small. Sometimes, you know, they can be 5 meters, 1 meter, and they barely come up in the image. It's a tiny, tiny dot of light. And at that point, it's hard to tell whether the asteroid exists at all. It's so dim that it seems to blur into the background of your image. It might just be light that's in the sky already, or just random noise. And at this point, it becomes really hard to tell what the trajectory of it is, because we can't precisely determine its position in the sky. That's when we have really useful things like the Very Large Telescope in Chile, very creatively named. It's very big, so they called it Very Large, which is the biggest telescope currently on Earth. I can see really, really, really dim and really far away. Our survey telescopes, there's a system called Atlas, which are designed to automatically, without even a person controlling them, just scan the night sky. They could see something like a 10-meter asteroid at the distance of 10 times further than the moon. If you picture something that's 10 meters big, like a bus or something, seeing that 10 times further away than the moon is crazy. So soon they're building the extremely large telescope right next to the Very Large Telescope. and that will be able to see things even further away. So ultimately, yeah, the method is still the same, no matter how far away it is. It's really about how bright it is and if we can really resolve it in the image. That's the important thing. Thank you.
Thank you.
Okay, and last question from Vittoria again. Portella della Ginestra Institute.
We are ready.
Hello, my name is Richard. How do they know if an asteroid is coming towards Earth?
Yes, great question. So this is the ultimate point of our whole office, of the whole planetary defense, to see, okay, there's a rock in space. Is it coming towards Earth? Is it dangerous? So when we do this whole process that we've been discussing, where you find the asteroid and then you work out its trajectory, then the next point is to run that trajectory forward in time. So we have these amazing supercomputers here at ESA and also at NASA that have a whole model of the solar system with all the planets, all the moons, and lots of asteroids in as well. And what we do is we place this asteroid that we found in this model and we run it forward in time. And this asteroid will whiz around the solar system on its journey. And as it does, it will feel the gravitational effects of all the bodies in the solar system, from the sun and maybe other planets as well, if it goes near them. And we can run this simulation, this model, forward hundreds of years into the future. And as we do that, we see, will the asteroid pass near the Earth at any point in time? It may seem like when you first do the observations that the asteroid will miss the Earth, but maybe if we use our very advanced models, it might be that the asteroid comes back towards the Earth in 10 years' time. So just by looking at the observations alone, unless it's coming straight directly towards you into your line of sight, it can be very hard to tell just from the images alone whether the asteroid is going to be coming towards the Earth. So we have to run these big simulations and run them hundreds of years into the future to see whether it will come near the Earth. It's important to note as well that this trajectory, we don't know precisely. There's a bit of uncertainty. So it might be moving a bit faster, a bit slower. It might be a bit to the right, a bit to the left. And over time, this uncertainty grows as you go through time. So we also to take that into account as we run this trajectory forward into the future and see whether it's possible, in the best case or the worst case, this asteroid will come close to Earth. So this process is really, once we have the observations, we have to look hundreds of years into the future to see if there's any chance it will come close to Earth. So big computers, lots of big maths, and a lot of fun for that one. Thank you.
Okay, so thank you, Charlie, for your time and for sharing your precious knowledge with all of us.
I try.
It's been so interesting, and it was also easy to follow.
Good.
Thank you, because I think everyone has enjoyed your discourse. So thanks to everyone from me, Francesca. Goodbye.
Thank you.
Thank you,
partners, and see you next time. Bye-bye.
Thank you so much. Goodbye.
Bye. Thank you, everyone.
Thank you. Bye.
Bye.
Bye.